Now let's discuss the preparation and reactions of esters. So we've actually talked about several of the methods to make esters, both in Chem 2131 and in Chem 2132. First, if we take a carboxylic acid and deprotonate it with a base like sodium hydroxide, we can add an appropriate alkyl halide to it to get an ester. Note that this is an SN2 reaction, which will only be very good with primary or methyl halogens. We can also prepare esters, as we've just seen, from acid chlorides and acid anhydrides. The ester reacts with both of them in the presence of base or without to produce an ester. This particular ester is known as isoamyl acetate, and it is actually the main component of artificial banana flavor. A much more common way to prepare esters is by a reaction known as Fischer esterification. Fischer esterification takes a carboxylic acid and treats it with an alcohol in the presence of a catalytic amount of acid. This exchanges the OH group for the alcohol, removing water as a side product. Like several other reactions we've seen this semester that have water produced as a byproduct, this equilibrium can be driven towards the product side by continuously removing water from the reaction mixture, either by a Dean-Stark trap or some other chemical means. This ester is called methyl salicylate, and it is the main ingredient in oil of wintergreen. If you've ever had wintergreen flavored gum, or if you've used tiger balm, you've smelled or tasted methyl salicylate. This is a good mechanism to practice on since it occurs under acidic conditions and has numerous proton transfers. Show the mechanism of this Fischer esterification, then when you're done, check your own work on page 925. Be careful with the proton transfers. One of the primary reactions of esters that we need to discuss is called saponification. Saponification occurs when we take an ester and cleave it using a strong base like sodium or potassium hydroxide. This is often followed up by treatment with H3O+ to reprotonate the carboxylate derivative that's formed, giving us a carboxylic acid and the cleaved alcohol. We've actually shown a mechanism for this reaction before, but it's still a good one to practice. If you want to try this, draw a mechanism out, then check your work with page 927 of the Klein book. The main utility of this is actually one that's fairly familiar to most people. It's soap making. The way you make soap is you take fat and you combine it with sodium hydroxide. Fats and oils are actually esters. They're triesters of glycerin or triacylglycerols. Once we do this, we're going to be cleaving the three ester groups off of glycerin to produce 3 sodium carboxylate salts. We'll also get glycerin as a side product, which is often left in the soap as it's a good way to moisturize the skin. So if you have a long-chain fatty acid and a polar head group, that's a surfactant, and that's what we know as soap. We also need to discuss the reactions of esters with strong nucleophiles like organometallic reagents and lithium aluminum hydride. We've discussed some of this in 2131, and we'll also introduce a new reagent which will allow us to selectively reduce esters to aldehydes. In 2131, what we saw is that if you treat an ester with lithium aluminum hydride followed by aqueous workup, you get a primary alcohol and the alcohol group from the ester that will be cleaved off when this reaction occurs. The same thing happens if we treat it with an organometallic reagent like a Grignard or organolithium reagent, although in this case we get a tertiary alcohol and we've cleaved off the ester as a leaving group as well. If we want to do a selective reduction to an aldehyde, we need a reducing agent which is strong enough to reduce the ester, but unreactive enough that it's not going to react with the product aldehyde. The one we're going to use for this is a little different than the prior selective reducing agent that we saw. This one is called diisobutyl aluminum hydride, but it reacts in much the same way. Here we've bulked up the aluminum atom so that its reactivity is reduced. It can only donate 1 hydrogen atom to the ester carbonyl group, which means that we cannot further reduce the aldehyde once this reaction is complete. There are some interesting practical applications to this chemistry as well. Many insecticides and nerve gases target ester cleavage pathways within the body. For example, this molecule is acetylcholine, which is a very common neurotransmitter throughout the smooth muscle of the body. Acetylcholine is released into the synapse, where it causes muscle contraction. After acetylcholine is released, an enzyme called acetylcholinesterase, or ACHE, will hydrolyze acetylcholine back into choline on the right and the acetate ion on the left. This is one of the most efficient enzymes in nature, being able to catalyze the cleavage of over 25,000 molecules per second. The way this process works is as follows. Acetylcholinesterase has an OH group at its active site. The enzyme undergoes a transesterification process with acetylcholine, which places the acetyl group onto this OH group. This effectively inactivates the enzyme, meaning that it's unavailable for cleavage. If this enzyme is not able to cleave acetylcholine, the acetylcholine will stay in the synaptic gap, causing continuous muscle contraction. The enzyme hydrolyzes the acetyl group at the active site in a matter of microseconds, regenerating it to react with more acetylcholine. Chemical compounds which target this process are known as acetylcholinesterase inhibitors. Just as a reminder, here's acetylcholine. Here's one of the most potent inhibitors of human acetylcholinesterase that humans have designed, a molecule known as VX. This compound has a fatal dose of about 10 milligrams absorbed through the skin. I've color-coded the two molecules so that you can notice some molecular similarities between the two. On the left, we have an alkyl group, which binds to the active site. This is attached to an electrophilic atom with a leaving group. Notice that the P double bond O group of the phosphonate can behave very similarly chemically to the carbonyl group of the ester. There's a CH2 spacer, followed by an ammonium ion at the end. Because these molecules have similar molecular features, they'll both bind tightly to the active site of acetylcholinesterase. When acetylcholinesterase binds, it transfers the acyl group to the enzyme. When VX or another molecule like it binds, it transfers the phosphate group to the active site. While the acetyl group can be hydrolyzed in microseconds, the phosphate group takes days to hydrolyze. That means this effectively permanently inactivates the acetylcholinesterase enzyme, which means that acetylcholine builds up in the synapse, causing continuous muscle contraction. Or, as put by Nicolas Cage in the 1996 blockbuster The Rock,
it's a cholinesterase inhibitor. Stops the brain from sending nerve messages down the spinal cord within 30 seconds. Any epidermal exposure or inhalation, and you'll know. Twinge at the small of your back as the poison seizes your nervous system. Do not move that! Your muscles freeze, you can't breathe. You spasm so hard you break your own back and spit your guts out. But that's after your skin melts off.
Oh my God.
Well, I think we'd like God on our side at the moment, don't you?
Of course, some of that is artistic license. VX doesn't actually melt your skin off, but it does cause many of the other symptoms that Nicolas Cage mentioned in that clip. Next, we'll move on to talk about the final of the carbonyl family of functional groups, amides, and their cousins, nitriles.